presentation on groundwater control, both informative and enjoyable. And a few items before we get started. All attendees are muted to avoid feedback and enable everyone to hear the presentation, but questions are welcome. Questions will be submitted can be submitted through the chat window as shown on this slide, and will be answered at the end of the presentation. Due to the large number of attendees, there will likely not be enough time to answer all the questions live, so unanswered questions will be addressed in a follow-up email. Also, please note that the session is being recorded. Lastly, a 1-hour PDH credit is available for attending this session. Please respond to the poll at the end of the session to register for the credit. And now, I'd like to introduce our speaker for today, Paul Schmall. Paul is well known throughout the industry for both his engineering and construction achievements, as well as his giving back to the profession through his active involvement in professional societies. Paul is currently Vice President of Business Development for Keller and was previously the Chief Groundwater Control Engineer for Moore Trench. He holds degrees from Bucknell University and the University of Nottingham. Paul has over 30 years of experience in geotechnical engineering and contracting, with extensive experience with complex groundwater control, grouting, and ground freezing projects. He has authored more than 40 technical papers and articles and co-authored the 3rd edition of Construction Dewatering and Groundwater Control. Paul has been the recipient of many awards, including the 2015 Wallace Hayward Baker Award, the 2014 Engineer/Instructor Award of the New Jersey Society of Professional Engineers in Construction, and is the incoming president of the Moles. I will now turn over the session to Paul for his presentation on groundwater control. Take it away, Paul.
Thanks, JD. Okay, I think you can see me now. All right, thanks for that generous introduction. So, in struggling with, what should be the presentation or a presentation title, I thought, you know what, if this hour brings you 5 little nuggets of wisdom on groundwater control, I think I've done my job, because it's actually very difficult to cover this, because here are all the things that Keller does. Basically, we do everything. There's nothing out there that we don't do, but when you boil it down, you could put those different techniques and technologies into a number of different categories: ground improvement, earth retention, deep foundations, and then the last one I would call groundwater control. And groundwater control may consist of these different techniques that you see on the screen. So I'm going to talk about these techniques today in the next hour. So I'm trying to cover a lot of ground. So this is one of these presentations that's going to be 1 inch deep and 1 mile wide. So I am also assuming that everybody really has a familiarity with these techniques. So I'm not starting from square one with every one of the techniques and describing the technique and the pros and cons and the applicable soils and et cetera. I've stepped beyond that, and I'm assuming that everybody has passed Geotechnical Construction 101. So my suggestion is if I'm skipping ahead too much and you want more details on one of these techniques that I'm talking about, go to Keller's website, because there's reams of information there on all of these techniques. So in this big category, this big fuzzy category of groundwater control, there's really 2 different approaches. We can be lowering the groundwater, or we can be building barrier walls. And I kind of think of it like we're working with the groundwater, or we're fighting it, we're embracing it, or we're working against it. But it's two kind of different philosophies. And sometimes there are places where there is this overlap where the combination of these things is the right solution. So what I'm going to talk about is 3 areas of groundwater control: groundwater lowering, which we'll refer to as dewatering, that's the simple word; construction of barrier walls or cutoffs; and then managing seepage into structures, into or through structures, or excavations. So this is a lot of stuff here. So like a rat approaching a large block of cheese, we're going to start from the top and we're going to nibble our way down. So we're going to talk about dewatering first. And I think most people intuitively know that the purpose of groundwater lowering or dewatering is not just to eliminate the inflow of water into an excavation, but also to improve the characteristics of the ground. And the photographs illustrate that very well. Same site, same ground, wet versus dry. Or in geotechnical language, more appropriately or more, let's say precisely, difference between saturated and drained. So you can see the difference. It's workability, it's stand-up time, it's stability, it's shear strength, it's slope stability in excavations. So this is same thing, drained versus wet. This is actually lower Manhattan silts that I will often refer to as bull's liver. And if you're from around New York, you know what bull's liver is. But if you're not from around New York, you have no idea what bull's liver is. Bull's liver is the native non-cohesive silt of lower Manhattan. And then this other example here of my wet versus dry. This is actually fly ash. We're doing a lot of work these days working in fly ash and coal combustion residuals with because of the federal mandates to close all of these fly ash ponds across the country. So the fly ash is interesting because it really amplifies, it exemplifies, it amplifies all of these unfavorable characteristics of fine-grained, non-cohesive soils that we learn about, undrained shear strength, capillary action, liquefaction susceptibility, which is what you're looking at in the pictures here. So with the purposes of groundwater lowering, like I just said, it's the one that I think people think of maybe first or foremost, saturated versus drained conditions, stability of excavation side slopes. Sometimes it's for the purpose of taking lateral loads off of supportive excavation. Then there's also the purpose of preventing heave or blowouts or quick conditions within an excavation. But the biggest one, or the most critical one, at the bottom of my list here is controlling seepage and the migration of fines. My scary example is this. This is a project, this was in Cologne, Germany. This was probably about 10 years ago now. It was a dewatering mishap. It was a tunneling project, a deep shaft excavation, and they were pumping water from inside of the excavation, like you see in the figure on the right. But they were pumping, we call it open pumping, just throw a pump into the excavation, pumping the water, pumping a lot of water, and maybe with every gallon of water they were pumping, they had a little bit of sand that was in the water. So over time, a lot of gallons equals a lot of sand, and you've moved a lot of material. And what they believe happened was they lost the passive toe of the slurry wall because of piping with inside the excavation, and then the shaft collapsed. Okay, this is my extreme example of migration of fines with improperly executed dewatering or improperly executed groundwater control. So the big thing, all those other things, those purposes that I mentioned to you before, they may be very significant purposes, but they don't have catastrophic ends such as the migration of fines. So this is a more realistic, more, let's say, more day-to-day example of migration of fines. It's an excavation where a contractor installed widely spaced dewatering things, and it should have been closely spaced dewatering things, and they had water flowing into the excavation, and the water is bringing sand into the excavation. Bad things happen where the ground comes from when the ground migrates. And this is like beach sand here. So the beach, just remember this, the beach is a great place to go on vacation. It's not a great place to work. And in the context of groundwater control, just think of beach sand as your example of these are conditions to be wary of. Beach sand is clean, it's uniform, and it's loose, which means when you have a little bit of water in it, it will run. How many people have dug a hole at the beach? Everybody's dug a hole at the beach. You know what happens when you get an inch below the water? It just comes running in. that type of soil is highly susceptible to movement. So you see this picture. If you don't want this to happen on your project, there are too many engineers that don't want this type of occurrence on their projects, but too many engineers that are apprehensive to step into the realm of the contractor's means and methods. They don't want to specify too much because they don't want to specify contractor's means and methods. But in a situation where you're susceptible to this kind of thing, there are plenty of ways of writing a specification to mitigate this type of occurrence. So when we have the need for lowering the groundwater, we're in soils that are susceptible to movement. We do this thing that we call pre-drainage dewatering. What does that mean? It means we're installing wells, well points, or ejectors, the common tools of dewatering, in order to pre-lower the water level within an excavation prior to the excavation. It's key that you construct the devices properly so that they disallow the migration or movement of or erosion of the natural soils. That's all in the filter pack design. And then we will physically drain the soil, which is what we call dewatering, or we will reduce the pressure underneath an excavation. That's what we call pressure relief. And this will permit excavation in dry soils or prevent blowout from below. Okay, that's pre-drainage dewatering. Dewatering is easy when the soil is free draining. I should say it's easy, it's readily achieved. Maybe it's not easy, but it looks like, it's well done. It's readily achieved. The end result, it can be achieved readily if the soil is free draining and there are no impediments to drainage, no impediments like layering within the soil. Okay, and when the amount of recharge that may be present at a site can be accommodated by the dewatering system itself. Okay, in the photograph here, you see a picture of an excavation out in the middle of the river. You can tell that it's clean, sandy soil out in the middle of a river. And most people would say, whoa, you can't do that. You got, you're right there. You got your recharge right on top of you. It's done all the time. Dewatering contractors do this all the time. They understand that if the dewatering system has the capacity to handle and accommodate the recharge that may be available locally, it can be done. So this is what can be readily achieved. When it is difficult is when you're in a situation where the soil doesn't want to give up the water. You're in fine-grained soils that don't readily give up their free water, or you have impediments to drainage. Water has to flow vertically for dewatering or groundwater lowering to occur. And when you have horizontal layers that prevent the flow of water to flow vertically, that's an impediment to drainage, like you see in the picture in the upper right. And when you have a condition like what you have in the upper right, then you subsequently have a condition that you have on the lower right, where this is an excavation that has basically been abandoned because got down to an interface where coarse material is over fine material and the water just wants to flow into the excavation. So I mentioned when dewatering is readily achieved, the dewatering system can accommodate the recharge. When you're in low permeability soils and you have a dewatering system really that's going to draw very little water out of the ground, if you have more water than that capacity that is introduced to the situation, say from like leaky utilities or something like that, that's when you're going to have problems. And you typically have problems in low permeability soils because of an amount of recharge to the site that overwhelms the condition or the situation or the capacity of the dewatering system. So these are a number of projects here. I'm in fine-grained soils. I want to say beware of the non-cohesive silt material. Every one of these pictures, there's a story behind it, but most of these stories really go back to somebody thinking that, oh, you know what, it's low permeability soil, it's not a big deal, because somebody will say there's quote, not a lot of water in the ground. That's kind of like the old school way it's referred to. Oh, there's a lot of water in the ground over there, or there's not a lot of water in the ground over there, whether it's high permeability or low permeability. When it's low permeability material, there may not be, quote, a lot of water in the ground, but the material may not be stable at all when it is saturated. So that's when you have these horror stories, these unfortunate occurrences. So this is my most common dewatering misconception, and that is, if there is, quote, a lot of water in the ground, then the need for dewatering should be taken seriously. Okay, that's not the way to gauge it. It should be based on what is the stability or the likely stability of this ground when saturated, and that should determine if dewatering should be taken seriously or not. So how do you know? How do you flag when you have these types of soils? I'm going to give you a little quick recipe. Okay, the typical non-cohesive silt that pops up in various areas around the country typically has a grain size distribution curve that looks like 10% silt or 10% sand, 80% silt, 10% clay size particles. And of course, there's a plus or minus with that. But then there's a very low plasticity index, typically like less than 3. So this is Manhattan bull's liver silts, the material that I showed you before that's around the World Trade Center, that part. No, very, very well-known unstable materials. Providence silt, it's also the same grain size distribution of typical fly ash, which is ridiculously unstable material. And then beware of unanticipated sources of recharge. Like I mentioned, particularly when you are working in low permeability soil and the ground, your site has very little ability to absorb any kind of recharge that is introduced to the site, say from leaky utilities, or there's runoff that finds its way to one particular area of the site. This photograph here is an unfortunate condition on a site where there was water that was flowing through filled ground and filled ground below the water table. It's a mixed bag. You just don't know what you're going to have. So beware of water and fill, and especially in low permeability soils. And then when you're doing dewatering in urban areas, you're always going to have water treatment in urban areas. You have contamination everywhere in urban areas, and even if it's not on your site, you have contamination across the street. It's coming. So there are reams of water treatment technologies that you can use to address the water conditions on any site. You need to know what's the chemistry, not only what is the chemistry of the contamination on site, but what is the natural groundwater chemistry. Do you have fouling agents such as iron in the water, high iron in the water, which tends to gum up treatment equipment? You need to know the permeability, not just the permeability, but the aquifer parameters like permeability, radius of influence, et cetera, so that you could design a dewatering system, because really with the treatment, you need to know what's the flow rate. What's the flow rate? Because that's going to drive the cost of the treatment. And then on dewatering systems, you have to have built-in redundancy so that you can maintain, swap out equipment, change media, et cetera, without ever having to shut down the treatment system. It's not like you're treating the water at the corner gas station. You have to have a lot of built-in redundancy with the system. And then sometimes the construction water on the site is the most difficult thing to treat for, actually. So now that was it for dewatering. Okay, that was the crash course, 1/3 of an hour. Okay, so now we're going to talk more about groundwater exclusion, cutoff walls, and barriers, like I mentioned. So we're kind of like on groundwater control area number 2. So the first thing that I want to talk about is the concept of the bathtub excavation. So I use that term to describe these excavations that have impermeable perimeter walls that extend down to a natural cutoff stratum, low permeability layer, or if there is no stratum, cutoff stratum, horizontal cutoff stratum within reach, there's a man-made bottom. But it's a bathtub, it's a watertight excavation. So why would you do this? You would typically do these bathtub excavations. You see them in urban areas where there is concern about contamination migration, the presence of compressible soils, such that if you lowered the groundwater 300 feet outside of the site, you're going to see settlement settlement out there of those structures. You may have timber piles. Boston is Boston, New England, well-known urban areas where you have timber piles that can't be dried up and then resaturated because you get biological degradation of these wooden piles underneath these old historic structures. Sometimes you make a bathtub excavation when there's an issue with extracting water out of an aquifer, or there's an issue with disposing of the water or the mechanism of disposing of the water. Sometimes, and I'll talk about an example or two, a situation where if you were going to dewater an excavation, it's just too much water to handle, to dispose of, to get rid of, to pump, to economically dewater. So when you have these bathtub excavations, there's really two components. You have perimeter walls that are vertically advanced, vertically installed perimeter walls, and then you have a bottom. And we're going to talk about the man-made bottom for these bathtubs. So you can see my icons here, the techniques that you would use for the construction of these perimeter vertical walls. Steel sheet piling, but I'm not going to talk about steel sheet piling. You guys don't need me to talk about steel sheet piling. Slurry diaphragm walls, secant piles, deep soil mixing, and then I would say less commonly, but in special circumstances, jet grouting and ground freezing. You see ground freezing when it's more like, instead of a bathtub excavation, it's a bathtub shaft. It's a very deep excavation. It's a tunneling excavation. So let's talk a little bit about those. So this is a good picture of slurry diaphragm walls. So with slurry diaphragm walls, and for all of these things, I'm going to try and show you the tools that are used for constructing them. With slurry diaphragm walls, you have a couple of different tools depending on the depth, the ground conditions. The simplest and most basic is a cable clamshell, a cable operated clamshell, which could get you typically to about 120 foot in depth. When you're you could be in a reasonably wide range of soils, but if you get into boulders or boulders with the clamshell, you're using a chisel, which some people would refer to as a barbarian technique for excavating slurry walls. So the cable clamshell, the next step above that is the hydraulic clamshell. We have been to 250 foot depth with hydraulic clamshells in stiff soils. The hydraulic clamshell, as opposed to the cable clamshell, the hydraulic clamshell is a steerable. The frame is steerable, so you can steer as you're excavating. Built-in inclinometers. You know where you're going with the hydraulic clamshell, but you're going to get to 250 foot depths with both the clamshell installations. You're going to have end stops. You're going to have water stops. When you jump to the next tool, the hydromill eliminates the need for end stops and water stops. The hydromill is rotating cutter heads that will advance through a much wider range of conditions, and the hydromill can chew through a lot of different things, including boulders, seat it very deep into rock. We've done a lot of hydromill work in the last, since we've been using we first hydromill project that we did that was done in North America was the Chattahoochee Tunnel, and that was the first time we used a hydromill, and since then it's been our tool of choice because it delivers a higher end product. You don't have the end stops. Your closing panels are cut concrete to concrete, and it's just a better, higher quality end product. So we've done those walls to 270 foot for perimeter walls. We've done load-bearing elements, where it's like a deep foundation element done with a hydromill to 365 feet. And a lot of the conditions that we have experienced are, at the time, we're very much first. We have lots of boulders, high permeability, overburden, hard abrasive rock, low headroom conditions, very steep rock surfaces. I think we've been through it all. We've used the hydromill for the vast majority of our work, and we'd be very happy to share our experiences with you with all of these techniques, to be honest with you. But we have particularly our resume with diaphragm walls is outstanding. One of my favorite projects is this Blue Plains Tunnel, 42-inch walls, 175 feet deep, with blockouts built into the wall, so that once the shaft was excavated wet, could punch out the shear plugs into the wall, so that you have the tremie that was poured at the bottom of the shaft was keyed into the wall. We do that typically on these diaphragm walls. So you can see some of the big cages that were used here for some of the larger multi-bite Y panels that were done on this binocular shaped shaft. So secant piles are advantageous when you have steep rock, very steeply dipping rock surfaces, or limited site access, you just don't have room on site to make cages and lift cages where you would with diaphragm walls. So the secant piles, obviously limited with depth because of borehole deviation, and arguably probably about 80 foot is maximum depth, plus or minus depending on what the ground conditions are. And you can see in the photograph on the right, it doesn't do justice to it, but that was that 2nd Avenue subway, which there was a very steeply sloping rock surface on that site. And then there's jet grouting, which can be used for shafts. And the photograph on the left, it was used for not only the perimeter sidewalls, but also for the bottom seal on that shaft. You also see jet grouting used for on these bathtub excavations when there are discontinuities in the wall. The typical bathtub is sheeting or slurry diaphragm walls around the perimeter, except where you have utilities running through the middle of the site and you have to close these windows. That's where you would typically see jet grouting as well. Jet grouting is applicable over a wide range of soil conditions, and like secants, it's susceptible to borehole deviation, which is probably its limiting factor. So if diaphragm walls, slurry diaphragm walls, and secant piles are replacement techniques, jet grouting and soil mixing are mix-in-place techniques. So the end product is basically a function of the in-place soils and the binder that you introduce in the process. So with soil mixing is appropriate for ground that's neither really very stiff or very dense, and no boulders or obstructions, and where your treatment depth is typically less than 40 meters. And for most soil mixing techniques, you need unrestricted headroom, because most soil mixing techniques are single stroke operations. So if you're going 100 feet into the ground, you need 100 feet plus of equipment to do that single stroke. But with soil mixing, I swear there are 31 flavors of soil mixing, and it's every contractor has their own special setup, and it really comes down to what's the tool that you're using to do the mixing, and all sorts of variations with the flights or the blades and shear blades on the tools. What's the orientation of the axes, and are you introducing jetting into the operation? You can mix and jet at the same time. So that's kind of how with all these different variations you get. I was kidding about the 31 flavors, but there's a whole host of different techniques. There's different techniques and to be honest with you, different acronyms for all of them. So we're going to talk about single axis mixing, multi-axis mixing, CSM, and TRD. Okay, and I'll get into these one at a time. But when you look at these, we're constructing columns, pairs or triplets of columns, panels, and then continuous trench with mixing. So the first one I want to talk about is what is known as cutter soil mixing, or CSM. It looks like, the tool looks like a hydromill, because basically it's the same cutting wheels as a hydromill uses. But it is, instead of displacement with these horizontal axis rotating cutter wheels, you're mixing the soil as you penetrate down and introducing binder on your way back out. It's a more aggressive mixing technique, so it's applicable to a wider range of soil conditions. And I think you can see you can penetrate a lot of things with these cutting wheels. So we've done this technique up to depths of 130 feet. I believe the equipment is capable of going to about 165 feet. And the photograph that you see on the right is a structural CSM wall where you mix the soil in panels and then drop beams into the panels for your reinforcement. So the next technique would be multi-axis mixing, and there can be 2 different vertical axes. There could be 4 or 5 different vertical axes, and that's a configuration that lends itself very nicely for making walls. So you see on the picture on the right, we're trimming a soil mixed wall within this excavation. And then TRD is short for trench remixing deep. And I have to show you this cartoon here to show you how the process works. Basically, a cutting post is advanced to a design depth. Here's the cutting post that's being advanced by the machine. Watch it as we're advancing the cutting post, and then we advance it in sections. And you get all of the sections in place, and you get the post down to design depth, and the machine the depth can vary as it works. But you install the post, the depth like so, and then the crawler advances along the alignment of your cutoff wall, and the post cuts, and you mix binder into the material. This technique is very good for making very homogeneous soil mix. You will mix very thoroughly from top to bottom within this trench, which is not all soil mixing techniques have that same homogeneous mixing as the TRD does. Beautiful things about the TRD: there's no joints, and it's always the joints in cutoff walls that are the point of weakness. There's no joints. It's thoroughly mixed. It's a relatively low headroom piece of equipment. How I said most soil mixing techniques are single stroke, very tall piece of equipment. This is a low headroom piece of equipment, which is good for working very close to water, or very close where water is within a couple feet of surface, and where there may be more concerns about working platform stability. This TRD can also key into weak rock. It can key into stiffer layers. It's a pretty versatile tool. You can see in the photograph here, this is another structural wall, a TRD, where beams have been placed into the trench following the mixing. And you think of it like beams and lagging. It's beams and soil mix. So that's the TRD. So now that brings us to our next chunk of techniques, where we're talking about the bottom seal, the bottoms for these bathtub excavations. So the bottom seal, I use this term bottom seal. You could think of it as a pre-installed bottom to these bathtub excavations, as opposed to like a tremmy bottom. So it's pre-installed. Generally, the larger the excavation, the more square footage, the more a bottom seal makes sense rather than a tremmy. And the techniques that we're going to talk about here, I'm going to call them vertically advanced or vertically installed partial height methods. And those are jet grouting, permeation grouting, and soil mixing. So these are 3 different configurations of bottom seals. We'll call the one on the left, we'll call that a massive bottom seal. And if your design relies on basically just the weight of the bottom seal to counteract hydrostatic uplift. These massive bottom seals can be pretty darn thick to offset the hydrostatic loading, which leads us to the necessity for the next type of bottom seal that you see in the middle here. This may be a thinner bottom seal, but it's tied down to withstand the hydrostatic uplift. And then the bottom seal on the far right, we're going to refer to that as maybe a deep blanket seal. See the same excavation subgrade for all of these scenarios, but this bottom seal, deep bottom seal, relies on the weight of the material above that bottom seal to withstand the hydrostatic uplift. But the bottom seal itself is relatively thin, which is why we'll call it a blanket. So the first two are more like structural bottom seals, and the one on the right is not so much a structural, but call it a hydraulic bottom seal, which typically you're going to see these techniques used for these types of bottom seals. Not all the time, but most of the time. So it'd be a jet grouted bottom seal that may be on the far left, and then the middle one may be jet grouted or soil mixed and tied down, and the one on the far right may be permeation grouted or it may be jet grouted, but most of the time it's going to be permeation grouted. I kind of like the one on the far right because in a situation where the groundwater control may not be absolutely perfect, you have some real estate above the bottom seal to draw the water out of the excavation in a controlled manner, which disallows the migration of fines so that it is properly dewatered. Okay, so this is what some of these bottom seals may look like in real life: jet grouting and soil mixing and permeation grouting. So there are a number of considerations when you're doing bottom seals. These bottom seals, I think of the bottom seal as the riskiest thing that we do. There's a heck of a lot of quality control, a lot of procedures, a lot of everything that goes into to make sure that these jobs are done very, very well. You're looking at survey data from borehole deviation from a jet grouted array of holes for the construction of a bottom seal. So in just kind of in the context of jet grouting, we're concerned about borehole deviation. We're concerned about insufficient overlapping of columns. We're concerned about shadows due to borehole deviation and the borehole that may deviate into a previously jetted column. So it's going to blind you off from the column that you're intending to jet. So there's also variations in column diameter and variations in jettability of the ground at depth. And those are all taken into consideration into the design of a bottom seal. So here's a picture of a bottom seal on the left and the configuration on the right, the drawing on the right. And we have to be very concerned when we have vertical that meets horizontal. So when we have the vertical sidewalls that meet the horizontal bottom seal, there are ways of addressing that in your designs. Specifically, I'll give you one where you have bellies of sheets. You have to make sure that you have an individual jet grout column in the belly of every sheet. This is an old photograph. This is from Miami. I think this is the photograph of the last dewatered basement that was done in Miami. And I think this project was a project that pumped about 25,000 gallons per minute and got the water level down to about elevation -11 for the construction of a basement. So 10 years ago, you drive around Miami, you wouldn't see any basements. There's been a long history of failed grouting attempts in Miami. Bentonite cement can fill voids, but it can't displace the silt and sand infilling in the coralline limestone, which is the ground in Miami. It's all coralline limestone, but it's typically sampled with a split spoon sampler. So it tells you that it's weak, crappy rock that has some structure to it. Jet grouting can't erode it effectively, but what we find that works extremely well in Miami is soil mixing. Because in this weak material, it can be soil mixed very well and better than other techniques. So this is an example of one of many projects that we've been working on in the last 10 years or so. down in Miami to construct basements, deep basements in Miami. I think the largest of the jobs that we've done, about 130,000 square feet to elevation. So subgrade of the excavation, elevation minus 35. So that's 3 basement levels down, and with tie down anchors, CFA piles, 182 feet in order to tie down that that deep base slab. So this is how it's typically done from the surface. Perimeter walls that are constructed with multi-axis soil mixing, bottom seal single axis mixing, and binder injected in the target zone of the bottom seal, and then the CFA piles advance through the bottom seal in order to tie it down and provide support for the structure. So jet grouting is another example of one of these vertically oriented but targeted zone techniques that can be used for constructing the bottom seals. Here's a good example in this photograph. This is a cross passage for a tunnel. So we don't need jet grouting all the way from the ground surface all the way down. We just need jet grout from, say, the crown of the tunnel to the invert of the tunnel, and that's our target zone. So jet grouting is good for, hey, we just need it done from 95 feet to 120 feet, something like that. Works out very well for jet grouting. And here you see photographs of a project where this is a tie-in into a subway in New York City, and the groundwater level was just a couple feet above the top of the structure. Jet grout, basically a curb around the excavation to keep the groundwater out. But we don't have to jet grout all the way from the surface. We actually stabbed in micropiles and did contact lagging above the water table for the balance of the supportive excavation. This is a very cool project of jet grouting, another jet grout example. I love this project. This is Victoria Station. This is in London. And most of the tunnels in London are done in this London clay, not Victoria Station. There's alluvial sand and gravel sitting on top of the London clay, which is exactly where this Victoria Station upgrade occurred, and the jet grouting was done in that sand and gravel zone to create a canopy. You see this complex array of jet grout holes over the tunnel to create this canopy of jet grout over the top of the tunnel for the purpose of ground control and groundwater control. Very extensive array of columns, 2,400 columns. All the holes were surveyed, put into BIM so that the whole thing could be laid out. But the work was done from the surface without rerouting utilities and keeping the rail service undisturbed during the process. So there was places where you just physically could not get in to install jet grout columns everywhere. So those places could be addressed from inside the tunnel, but we don't want any surprises within the tunnel. So the work was done very intentionally to map where all of the possible windows could be in the jet grouted canopy over the tunnel, which is what you're looking at in this sequence of slides. Everything that's colored here is a potential window within the jet grout canopy, so that there's no surprise. It can be addressed from within the tunnel. And so there could be gaps within the jet grout canopy, but if it's within the bigger enclosed area, it's not a big deal. When you have a gap that is connected to the outside sand and gravel and you have recharge out there, then that is a big deal. And the way that they could tell that within the tunnel is when you had a gap that was enclosed, the water that would flow out of the jet grout or out of the gap would be warm water, because warm from the heat of hydration of the jet grout. And then if the water would flow cold or colder, it was connected to the outside source. That's the situation to be aware of, and the situation that has to be addressed adequately from inside the tunnel. So one comment on groundwater recharge, because we're talking about groundwater control. So that was about bathtubs. So we do these bathtubs when we can't lower the groundwater out of the bathtubs. But in some cases, you can you can re-inject water back into the ground to raise groundwater levels when groundwater lowering is a problem. There was an enormous job done in Copenhagen, an enormous tunneling job done in Copenhagen, where extensive groundwater recharge was utilized to balance groundwater levels, because Copenhagen's like Boston, don't lower the water levels beneath these old historic structures. Groundwater recharge has historically been a very difficult, challenging thing to do over the last 20 plus or for decades, because the recharge systems tend to plug. What we've learned in the last 20 years is that if you treat the water before you re-inject the water, and even better, if you get a clean, potable source of water, treat that water and re-inject it into the ground in a manner that the water has absolutely no particulates in it, and you do not aerate the water in the process of the water flowing back through the recharge system, it is relatively easy to re-inject the water level into the ground. This excavation that you see here was a large excavation that was intended to be a bathtub, and it had a lot of leakage, which lowered the water outside of the site and underneath one particularly sensitive structure that happened to be sitting on compressible soils. We put recharge wells in, treated the water before we injected it, and raised the water levels back up to where they needed to be. Recharge is an underutilized tool. It has a lot more places where we could be using it. So I talked about the vertical techniques, these vertically installed but partial height methods. Let's talk about methods that can be done at any orientation and any shape, like you see in this. So this is ground improvement for a cross passage, and in this array, this is considering ground freezing to be done for a cross passage construction for earth retention as well as groundwater control. So you would typically need these types of techniques when you're doing things like cross passages, like you see here, cross passages or adits and connector tunnels. And the first technique that I want to talk about is ground freezing, because ground freezing, probably the most diverse technique that I'm talking about today. It can be used for a whole bunch of orientations, vertical shafts, very deep vertical shafts, arches, cross passages, safe havens, mixed face freezes, and you can even install bottom plugs in shafts with ground freezing, and install the bottom plug with ground freezing and let the freeze pipes at the perimeter carry it as the shaft is being excavated down. Very versatile, can be done in any orientation that you can basically drill a hole. So it's also relatively insensitive to what the ground condition is, which makes it work very well when you're freezing through obstructions or filled ground, or freezing up to a structure. This is the project on the central artery in Boston, where the fill was frozen out in front of the jack tunnel box to stabilize it, render it impermeable, and give it stand-up time. We've used it several times for homogenizing a mixed face tunnel, where it was anticipated that it was going to be a hard rock tunnel, but there's a crappy section that's going to behave more like soil. Well, freeze it, and the tunnel boring machine will think that it's all rock. So a couple of things that ground freezing doesn't like, and people are concerned about and aware of: doesn't like moving groundwater, and it doesn't like man-made sources of heat. But I think we have those things licked, because with moving groundwater, we know how to profile the pipes, take temperature measurements in the pipes during the formation process, so we can see warm spots which may be susceptible to, or indications of, groundwater movement, and we can do grouting to reduce the groundwater velocities, reduce the permeability, which reduces the velocity in those zones, so that we can have closure without moving water conditions. And then where we have man-made sources of heat, we just know how to cool these sources of heat, or these sources of heat transfer. And that's basically what the concerns that you would have with ground freezing. Permeation grouting, you can do in it, like with ground freezing, you can do in any configuration where you can drill a hole. You can drill a hole and install a freeze pipe. You can drill a hole and install a tube of manchette pipe and do permeation grouting. We've even used horizontal directional drilling on numerous occasions for installing long guided tube of manchette pipes for doing permeation grouting. And sometimes we use that same technique for installing pipes for compensation grouting as well. So rock curtain grouting, I think, is also, I think that's fairly obvious. You can drill holes in any orientation in order to grout rock. And then we have also these, what I'll call non-structural cutoff walls, which, and I've kind of put these in order of like increasing cost, but also, and then increasing cost to the right, but moving to the left, you have increasing space requirements or increasing site access demands. So you have the slurry trench on the far left, you have the TRD, and then you have a vibrated beam, which is basically a beam that's vibrated into the ground, and you inject cement bentonite back through guides in the beam as the beam is extracted, and you overlap the penetrations with the beam. And then you could also have what we'll call the thin diaphragm jet grout wall, which is basically jet grouting where you don't rotate the monitor, don't rotate the tools. So instead of getting a column, you'll just get a fan pattern or like a panel of jet grout. So that can be used for a non-structural cutoff. Those are all non-structural groundwater cutoffs where there's no structural need. It's not going to serve as supportive excavation as well. DAC is Keller for data acquisition. DAC is a noun, DAC is a verb. We DAC everything. If it moves, we DAC it. Any and all of these techniques, we DAC them. We measure anything and everything that we can during the installation process with the equipment so that we have a record of what was done. We're monitoring what was done, and we can also use DAC to control some of the processes during the installation. But we want to have a nice record, and honestly, you know what? It allows us to communicate internationally within Keller, and you know, we have a job with these ground conditions, and here's how we did the work, and here's how it responded, and it allows us to share those experiences. So you'll see on the reports that you can see how much binder, how much rotation, how much penetration, how much pullback speed, rotation, etc. All those things can be monitored and somewhat controlled with the DAC process. So it's something that we do with all of these geotechnical construction techniques. So there are places where you can combine groundwater lowering with groundwater cutoffs. And typically you're doing that when you're going to address a difficult geological interface, like a coarse over fine situation where you tend to have water perched on top of that. That's one of those difficult draining scenarios. You could also elongate a flow path to reduce the flow rate into an excavation, which will also reduce the amount of groundwater lowering that you have outside of the excavation. Or you could extend your cutoff walls down to an aquitard to basically cut off the flow or significantly restrict the flow. And then you can allow for controlled collection of internal seepage by combining these things. One example here, this is a deep excavation that goes all the way down to rock. So this is a very deep, difficult interface condition where you're excavating through very permeable sands and gravels down to a impermeable rock surface, and you'll never get the water all the way down to the surface because you can't drain it down into the impermeable rock. So you get some amount of water that's at that interface. That's a difficult condition to handle unless you have some type of a cutoff wall. In this scenario here, we installed a slurry trench around the inside perimeter of the excavation from a bench before the excavation got down to the rock surface. So cut off the water with a slurry trench. And then we are currently working on the Hampton Roads Bridge Tunnel. We extended the walls of the launch shaft, or we refer to the peanut here, extend the walls down to a lower permeability stratum, which allowed us to eliminate the jet grout bottom seal from this excavation. So extend the walls down to a lower permeability stratum that acts as a significant aquitard or restriction to the flow of water. This was a cut and cover tunnel excavation where the work was done in largely coarse sands and gravels, but we installed sheets well below the bottom of the excavation to elongate the flow path that the water would have to travel to find its way up into the excavation, and then hang the dewatering system up on the inside of the excavation so the water has to flow around the corner and actually flow through a lower permeability silty sand at the tips of the sheets to reduce the flow. Significantly reduce the amount of groundwater lowering on the outside of the excavation, because this was in an area that had a lot of compressible soils, meadow mats, what we call them, in Atlantic City, New Jersey. And then this is a combination of a deep bottom seal with dewatering from inside, like I mentioned before, dewatering from that amount of real estate that's above the bottom seal but below the excavation subgrade, so that the water that flows into the excavation can be collected in a manner that doesn't allow the uncontrolled migration of fines. So that's what it looks like in real life. So my last section, which is a little bit shorter because I'm almost out of time, is control or management of seepage through or into structures. So when I say through structures, that is referring specifically to just the flow of water through dams. We expect and anticipate water to flow through dams. However, what you see on the right here, that's piping. Okay, this scares the living crap out of people that understand dams. And then so this is millions of dollars being spent on the left here to control this piping situation. And dams, this is why we install tow drains, we install relief wells, we install these passive devices that allow the flow of water through the structure. But what are we doing? We're making sure that the water flows in a controlled manner that disallows the migration of fines or the migration of soils. So it's kind of like the scenario, hey, are we gonna lower the groundwater, or are we gonna install a cutoff? It's with the dam, it's situation, are we gonna allow the water to flow through and collect it with relief wells or tow drains, or are we gonna cut it off with something like diaphragm wall like you see on the left, or the TRD that you see on the right. Photograph on the left is East Branch Dam. That was a 247-foot deep cutoff wall that was about over 2,000 feet long, $180 million contract for us. The longest we've done, I think, is 4 miles and 270 feet deep for a continuous wall. So there's the whole topic of seepage grouting that we just don't have time to get into. It is a field unto itself. Grouts formulated so that they will work under flowing water conditions and injected back into the structures to stop the flow of water through cracks or through faulty waterproofing, and provide semi-permanent waterproofing of the structure. Field unto itself. And then we have the whole concept of water flowing into excavations and water flowing unanticipated into excavations. This catalog of notable tunnel failure case histories, you can find this on the internet, but I can tell you very quickly, it reads almost like a comic book. Actually, I shouldn't say that because it's not funny, but it's a very simple read. And it's a number of repeat stories. Oh, hard rock tunnel. Oh, but we thought that was rock, but it's not actually rock. Soft ground, it's wet. Oh, and it's coming in on us. Open face digger shield tunnel in soft ground, and the story is, oh, we have wetness. We have water in the ground, and oh, the ground is flowing, and now, oh, we have a sinkhole. Defect in supportive excavation or a cutoff wall, and oh, we didn't know we had that defect. And once you get down there and expose it at depth under high water pressure in unstable soils, we have a lot of material flowing in. Oh, and look at sinkholes. So a lot of these it's really not a sinkhole unless a bus falls into it. You see, I don't know why, but there's all these pictures that are on the internet. Every sinkhole seems to have its own buzz. And then we have uncontrolled seepage and ground loss that may occur in these unanticipated inflow scenarios. And the story, you're going to think this is a shameless plug, but it's I don't mean this to be a shameless plug, but the story always starts with hiring the chief geotechnical contractor, and followed by having field personnel that don't have the skills to say, does this feel right? Anything that you do, all these ground improvement techniques and these cutoff methods, there's always some element of having data or seeing what the parameters are telling you, the installation parameters are telling you, and having somebody experienced to look at it to say, does it feel right? When it doesn't feel right and it's missed sometimes, this is what happens, these unpleasant scenarios, these ground loss conditions. And then it's whoa, and then we get the phone call because it's perceived to be a groundwater issue, because it is a groundwater issue, because these problems always happen because of the groundwater. And then we get the Houston, we have a problem phone call. So in these scenarios, when you have these problems, the conditions are always highly disturbed. Sometimes there's obstructions that flow into the newly placed ground or the infilled ground. There's nooks and crannies, and then you may have still flowing water conditions. So in order to respond appropriately, you can't go out and do a geotechnical. You got to respond and respond in emergency mode. So the geotechnical investigation has to be built into the response. So you have to just assume the worst in terms of disturbance, and assume that you're going to have some disturbed ground, some undisturbed ground, and then build the investigation into it. Usually I'm talking about like grouting methods, because grouting methods are usually the response. Even though it's a groundwater situation, sometimes pumping groundwater is the response. Many times grout is the needed response, because you're trying to replace ground. And then when you're going to do the grouting, and you really have to pick the right method, because you have one clean shot at fixing it. Because if that attempt didn't fix it, you've just left an obstruction for the next attempt. So it has to be handled very well, and very well with grouting. Ron Hoyer, God bless his soul, used to say, grout is slow and dumb, water is smart and tenacious. I don't think he was referring to grout not working, but I think it was more of a statement that groundwater will find you at your weakest, and it will find you your weakest place or your weakest moment, and it's very smart and tenacious like that. So with that, sorry, I went a few minutes over. Do we have any questions?
Hey, Paul. Yeah, we've got quite a few actually, but being that we're a bit over, I think what would probably be great is to answer them directly through email, because we've recorded all the questions, and we can get those back to those people. What I want to say right now is, as I mentioned earlier, there is a 1-hour PDH credit available for this session, and there's a poll you'll see on your screen right now. That if you want to get credit for the PDH for the hour, go ahead and state that you need it here in the poll. The first question is yes or no, and then if you do, go ahead and enter your email address, and we'll make sure you get that. And as I mentioned, Paul thought he was done with this presentation, but he's going to get a list of a bunch of questions that we'll get back to people on. So we captured all the questions that were entered in the chat. We'll get back to those folks. If you come up with something later, Paul's contact information is right here on the slide, you can see. And he'll talk with you about that or whatever you have. With that, I think we'll let it go. Paul, thank you very much. As always, interesting and informative, and some great photos. So appreciate you sharing that with us today.
Thanks, JD. Does everybody have to say the 5 things that they learned to get their PDH credits?
No, I think you gave a lot more than 5. So I think, yeah, I think they can pick 5 out of all those that you mentioned. Thank you. Good deal. Well, thanks everybody. Again, the polling will stay on the screen for a little bit here. Please go ahead and enter it if you need your PDH credits. Thank you again, Paul, and everybody stay safe and have a great day. Bye.
Thank you all.